If we take a beam model and we take into account the buckling analysis, we can say, okay, we can, as long as we can recognize something which is like a beam, like this one here, then we are fine. So initially we can do a buckling analysis with the beam elements, but be aware that what happens in here, in general, these are fixed boxes if the design is well. So you could reduce the buckling length to instead of from center point to center point, you could do a small modification, but by default that is not taken into account. And especially in the design phase, I would not advise you to do so. It is slightly conservative, but you might need that extra limit later on in your design. If we do this one, we also skip. So this is the first part is on beam buckling. Now we switch to plate buckling, which is almost the same formula, but that has some distinct differences. Plate buckling is basically what is the difference between a beam and a plate buckling? If we take the same, if we take a thin beam with the edges free, so not supported here in the edge, then I have exactly the same results as a Euler buckling beam result. But if I consider the edges to be supported some way, for example, if I have a plate section where the plates at the tips are supported by the other plates in the other direction, then we get something which we call plate buckling. And let's discuss now what the effect of that is. Then we can set up the same formulas based on theory and virtual work. If we go a bit further, then we will see that you have for plate buckling, it is slightly more complex, but you basically have something similar. We also have buckling shapes. So we have, this is the first mode, then this is the second one, and so on. But something strange happens compared to beam buckling. For beam buckling, the lowest shape is always the most critical one. For plate buckling, that is not the case. Let's zoom in a bit more to the results and to the formula. We do the same trick as we do with with the beam buckling formula. We calculate this back to some kind of Euler buckling stress. So that is the stress when something buckles. We have some kind of, if we rewrite this stuff, we basically see that we have, instead of, we recognize the same things, p squared E, instead of I, we have T divided by B squared, and we see here the Poisson ratio 12 and a factor of K. What is this K? This K depends on the buckling shape. Yeah, and depending on the value of the buckling mode, that has an effect on the K factor. Let's zoom in a bit more, because this is now a formula, but how does that look in a graph? If we take this K factor, then we will see that depending on the A to B ratio, sorry, I go back, A to B, that is the length A, so this one is A and this is B. depending on the shape of the plate, so the length compared to the width, so the A divided by B, we get something which is a bit strange if compared to a beam buckling results, because we can see that instead of with a beam where the lowest buckling shape is always the highest buckling risk, for plates that is different. You will see that you see that at the beginning with a width to length ratio of 1, so basically this is a square, the lowest buckling shape is the most critical one, because you see this is 1, the buckling risk of 2 is much higher, and 3 is even much higher than that. But if we take a shape where we have 2 times the width, so this is 1 and this is then 2, then you'll see that the second buckling mode becomes the lowest. So if we and so for 3 times, the third one is the most critical one, and so on. So what you see is basically the buckling risk does not depend on the length of my beam of my shape, but on the width. Yeah. So if we have a certain width with an increase in the length, I only shape, and the only thing what happens is that the most critical buckling shape varies, but the buckling risk remains the same. And how is that? If we take, for example, 1, 2, 3, and 4, maybe that explains it better. If I have here a top, and then here a bottom, and here a top, and there a bottom, you see what happens. So if this one is 1 and this one is 4, the lowest buckling shape is always a plate tends to buckle in a square. Yeah. So if I have 2 times the buckling length with the same width, then the lowest buckling shape is basically, this is then an axis of symmetry. And then here, if I make it 3 times, then I have also here 1. So basically the buckling shape is always a square, and the buckling risk depends on the width, not on the length. Unless the length gets shorter than the width, because then we end up in this section. Okay, if we then take into account, okay, we do the same trick as we did with the limit for beams. We assume an Euler stress, which is the stress at which the plate buckles. And if we then assume, okay, we take this Euler buckling limit, if we take for that the yield limit, then this one becomes sigma yield. And you say, okay, we just suppose, let's take that yielding and buckling, the buckling phenomenon occurs when you have a yielding limit, just to see what happens in my design. Then I see that I take for an yield limit of 240, if I fill in here 240, the K value is always 4, as you can see here. So if I have simple supported side plates, then my buckling stiffness K is 4. Then I have then here 4 divided by 12 divided by 1 minus 0.3 squared, so that is 0.09. So this is 90%. Then I get a limit of, when buckling and yielding risk is the same level, then my width divided by the B divided by T needs to be below 56. And if I use a higher yield stress, then of course this one increases, but the buckling limits stays the same. So I need to have a lower width to thickness ratio. Yeah, because I can allow a higher stress because the yield stress is higher, but I also have in order to be able to reach that higher yield limit, I need to use a lower maximum width compared to the thickness in order to prevent buckling. Yeah, so that is an important finding in the design. If I have higher grade steels, then buckling becomes more important. So I need more stiffeners. Yeah, so if I make a box with S235, then my yield limit, if I got then the yield limit difference is 1.5. I go from 240 to 360. That is exactly 50% more. So I could reduce the thickness with 50%, but I need to reduce the thickness, but I need much more stiffeners because I have 50% lower, less thickness, and I have a higher buckling risk. So I have also, instead of 65 times the thickness, I need to do 46 times the thickness. So that is, what is this? Maybe 20%. So I can reduce the plate thickness with 50%. That is true, but I need to have 1.5 times 1.2, maybe 1.70% more stiffeners. Yeah, so the distance between the original stiffener and the new stiffener is much more. And that is the consequence. Okay. So far we just took into account simple plate buckling. So we have simple support is everything SS, what we call it. So that is simple support. So I have a plate. There is no clamping at the edge. And so that is simple support, and that is the standard curve, and that is this one over here. What happens if I have all edges clamped? So both the initial part as the edges, then I end up with curve A, which is this one here. You can see that here, this limit, this is around 7 compared to 4 normal. So if I clamp all edges, I can increase the buckling, or I can reduce the buckling risk by 7 divided by 4, not more. And so that is good to know. And if I only have the one edge constraint and the other one free, I'm somewhere in the middle between the two. And on the other hand, what happens if I have one edge free? Then I have this curve, or this one, E, if I have this one free and this one simple supported. D is free and then this one is clamped. In general, if this one is free, then the rotation at the initial part turns out to be there is some stiffness compared to nothing in the free edge. So then I have a result where I have E instead of, so compared to a stiffness of 4, I have a much lower risk. If we take this into account, then we can do the same risk for plate buckling, where we can see that for a stiffener plus plate together, I can make there a beam. I can assume that this is a beam, and I can calculate the buckling risk. But I need to take into account the limits for simple plate buckling, because of this limit of what the other buckling limit. And we can now see, if we look now at this shape, we can recognize, okay, this plate is at the begin and at the end simple supported, but this one is here free, and this one is free, and this one is simple supported here. So I have a different limit length or a thickness divided by the width for this value compared to the one which is supported at the beginning and at the end. This one I will come later, and this one I want to show first this one, and then I come back. So if we take into account a plate which is internal with the stiffener, then I have this limit which we calculated here. We assume that Euler and buckling limit are the same. But if we take into account the free edges here, then I have, instead of this this initial curve what we had here, where's that one? So instead of a stiffness of 4, I have here a stiffness which is around 0.4. Yeah, so that is 10 times less. If we compare that into our buckling analysis here, for free edges, then instead of 56 and 46, I now have more or less the same formula, but then instead of between, so if this one is 56 for yielding, then this one can be only 18 times the thickness. And so depending whether it is I have an internal plate or a free edge, I have a different limit to take into account before buckling becomes a higher risk than yielding. Okay, so that is if we take into account only one direction. Let's go back to the two plates. In reality, we have plates which are a bit more complicated, especially for ships and marine sections. In general, you do not have only one stress compared, and then in the other direction 0, like you have with beams with top and bottom plates. In a ship section, you have both compression stress over the length and over the width. Furthermore, you will also have to take into account whether something is bending in both directions or it is uniaxial compression. And then the last thing which we also need to take into account is shear. So we now need to calculate the risk in one direction, the risk in the second direction, and the shear risk. And then we need to combine all these things. The shear curves is basically, the idea is the same. We have here a kappa value which depends on whether everything is hinged or everything is clamped, but the idea with the limit is more or less the same. So that is a simple one. And of course the buckling risk here is this initial curve that we already discussed with the lowest buckling factor. Okay, so if we take into account the different limits, then we have here the K factor is 1 for values where the length is higher than the width, and if that is smaller, then we take into account this effect and we square it. And for shear, basically we have the same effect with some correction for a factor for length and width, because there the effect does make a difference, and the standard value as well. So basically these curves, all standards, no matter if you use the DNV or ABS or Lloyd's or Eurocode, they basically are all based on these simple idea of comparing the buckling limit and compare that to a yield stress. Of course, they take into account different combination factors and different safety factors based on yielding and buckling, but the idea is always the same. If we have a beam, then we have here, it is easier. Here on top I only have compression stress and maybe some shear if I have also a load limit in that direction. Here I only have compression and some shear which comes from this load. How do you combine that? If we take this into account in a simple way, then you see that the buckling limit in one, so this is the direction 1 and this is direction 2, you will see that if we take a perfect square, this is the real buckling limit. So if I increase the load in the other direction, then this is my buckling risk. This is a single one, and depending on the limit on the other one, I get more or less a perfect circle. That is nice, of course, but we can do the same trick with the critical stress as sigma 1 or sigma 2 with the tau. But basically, what happens if we want to combine all of them together? And here we have some differences between the different standards. Some standards use here square, other ones use a higher factor, but also here the limit is the same. This new is the safety factor, and you see that you take the limit in one direction plus the limit in the other direction, and in shear you take all the squares of them, and that needs to be below 1. Yes, for plate buckling, this is the shape of the formulas for all standards, yeah, and what varies is this one and this one and that one, and sometimes they take into account, for example, what happens if I have tension in this direction, because then I increase some stability in the plate. But that is basic. That is more or less details. The basic idea is always the same here. Then something else, and as I told you with beam buckling, if a beam buckles, then there is no reserve capacity, and if you go above the yielding at a certain location, then your full structure collapses. But for plate buckling, that is different, especially if the buckling limit for a plate is lower than the yield limit. Suppose I have a very wide plate, so that the B divided by T is bigger than this 56. Then what happens if I apply a load on one edge? And then I might have initial buckling, but the edges the edges of the plate have still some stability because they are connected to the plate, to the side plate. So I can also take into account, okay, if I take at the edges the yield limit up till this 13 or 14 width, because if I have a plate buckling which buckles much lower, the linear plate buckling is a lot lower than the yielding of the full plate, then the edges still can go up to the yield limit before they buckle. So there is some kind of a correction factor for this. And then you get, in reality, so if you do that into a calculation, you assume that the edges go up to the yield. In the middle, we don't have any load, and then in the edges, it is supported again. And this is what we call here, this is the width, the maximum width between the plates where the yield and the buckling limits are the same. So that is the effective width. So if I assume that the buckling limit and the yield limit are the same, then the width I have, that is my effective width. So the effective width divided by 2. So this 56 divided by 2, this 56, which is from S235, divided by 2, is then this. So 56 divided by 2, that is then 28. Yeah, so 28 times the thickness here and 28 times the thickness there. There we can go up to the yield limit. Yeah, even if the plate is wider, I still have at the edge these reserve capacities left. Yeah, so if we take that into account, then you have a modification of your curve. If we also take into account the imperfection of the initial plate, we get some modification curve. So that is different between different standards. This is something you do have for crane structure, since you have a specific wheel load on top of a plate. They have a modification if we have a stress concentration or not a concentrated load, but then over a smaller area. So there's a correction factor for that. Or something like this. You can take this into account, but that is then something which you can take into account specifically for this situation under a crane wheel. Also here, you take the same limit, you take into account, then instead of the full plate, the full load over the plate, you take this more concentrated one. But the idea is still the same. We take into account the different risks in the different direction, we square them, and the total risk needs to be below 1. Okay. I don't know, this one went here. Again, we discuss what happens if we have a free edge in an ideal situation. So here we had 56 times the width is 56 times the thickness, and here it is going to be, the width is, if we calculate, is 18 times the thickness. Yeah, and that is because of this free edge. Because of this free edge, if we take that into account into the limit where we assume that yielding and buckling risk are at the same level, then this is the rule of thumb. If we need to take that into account in the Eurocode, for example, then of course these limits, these are the upper ones. You also want to be, you still prefer yielding over buckling. So instead of these top limits, you use something which is slightly lower.